Welcome to Maths with Bob. Today we're looking at lines and planes in 3 dimensions, and we're going to start with 2 dimensions just to show you how we actually get these symmetric equations, which look a bit strange, I guess, in some ways in 3 dimensions. Okay, so the first thing is we start off with the general equation of a line. Now, we hopefully know that, okay, this is the equation of the line here. Y minus y0 equals mx minus x0. Okay, so this is the general equation, okay, of a line with a slope of m through the point x0, y0. Okay, all right. Now, say instead of the slope, okay, we're given a vector in the direction of the line. Okay, so the vector in the direction of the line is this one over here. Okay, this is the vector in the direction of the line. Okay, you can see here, it's called v. It's ai plus bj. Now you probably hopefully remember that I and j are unit vectors in the, well, I is in the x and j is in the y, and obviously k is in the z, but we'll come to that shortly. Okay, so we now have, okay, if you like, a vector in the direction of the line v. Now it has to go through a point x0, y0. Okay, so we'll generate another vector called v over here, and it's going to go from x0, y0 to this general point x, y. Okay, so this is the vector here. Okay, so it's basically a free vector. Okay, a free vector from one point to another point. Okay, this is the free vector here, u. Okay, it's going from x0 to the general point x in the I direction, and y0 to y in the j direction, or I should say the y direction. This is the x direction here, obviously. Okay, so that is the, if you like, the free vector u. Okay, now, okay, these two vectors, v and u, they're parallel. Okay, have the same slope, and therefore their components must be proportional. Okay, so if the components are proportional, I'll try and get that out. Okay, basically we just do a ratio of the components. Okay, x0 or x minus x0 on A equals y minus y0 on B. And if you look at this vector here, the y over the x is just b on A, which is the same as the slope. Okay, so this is the starting of the symmetric equation generation in 3 dimensions here, the idea of, if you like, proportional components. Okay, we're now going to have a quick look at other ways of sort of thinking about equations of lines in 2 dimensions, and we're going to get some parametric equations. You can see here, these are the parametric equations basically, and you can also, there's still another way of using the cross product as equal to 0. Okay, but just at the moment, we're going to just have a quick look at how do we get the basically the parametric equations of the line in 2 dimensions, and we're going to extend that to 3 dimensions. Okay, so we've got v and u here. Okay, basically v is the line, well, it's a vector acting in the direction of the line, and this is u is actually a vector on the line, actually. Okay, and all we do is we just say, well, obviously, okay, so we have 2 vectors. Okay, they're acting in the same direction. Okay, and we say that, well, normally the vectors, if the direction is the same and they're not of the same magnitude, then one will be a scalar multiple of the other. We can say just like this, u is equal to vt. We think of t as like a parameter. So we just basically say then, well, okay, if u is equal to vt, then u, the coefficient of I, okay, if you like here, this is the x component here, x minus x0 must equal a times t. X minus x0 equals a times t. And the same for the y. Okay, y minus y0, okay, this is the y component of the vector on the line, must equal, okay, a scalar multiple probably of this other vector's y component b here. So y minus y0 equals basically bt. Okay, this idea of a scalar multiple, obviously, I mean the vectors, it's all to do with vector spaces, but basically the vectors have to, if they're acting in the same direction, okay, they are just basically either equal or multiples of each other. Okay, a scalar multiple. Okay, so we rearrange those and get x is equal to x0 plus at and y is equal to y0 plus bt. Now, these are, if you like, these are said to be the parametric equations of the line, and if you basically eliminate t, okay, just make t the subject in both cases, you'll end up getting this back here, our original equation. Okay, and you can see here that was a sort of a introduction to parameters, I guess parameters in a way, but we're going to actually look at this as well in 3 dimensions. Okay. Well, okay, in 3 dimensions, okay, we're going to basically say that the line has a, well, it's parallel to this vector v, ai plus bj plus ck, and it basically starts from x0, y0, z0, and to some arbitrary point on the line, and we generate, okay, it's a free vector u again, and we just say, okay, well, okay, these 2 vectors, okay, must be scalar multiples of each other to start with, but they, not only that, is their components must be proportional. Okay, and okay, so if the 2 vectors are parallel, have the same stuff, their components are proportional, and we get x minus x0 on A equals y minus y0 on B equals z minus z0 on C. Okay, so we get this one here. This is these are the actual symmetric equations for a line in 3 dimensions. Okay, it looks a bit strange, but this is how we well, state a line or give a line in 3 dimensions. Okay, it's a they're called symmetric equations. Line didn't work too well. I think it's that bump there that did it. But okay, so I'll come back to that in a minute. But obviously, if one is a scalar multiple of the other, you also get the x minus x0 equals at, and then we make x the subject. X is equal to x0 plus at, and y equals y0 plus bt, and z equals z0 plus ct. Okay, so let's see if I can get this circled. Okay, all right. So this is the parametric equation of a line in 3 dimensions. Now, if you eliminate t, okay, you'll end up getting back here. Here we go. Yes, worked this time. Okay, so this is the symmetric equations. Okay, or if you like, the equation of a line in 3 dimensions: x minus x0 on A equals y minus y0 on B equals z minus z0 on C. Okay. All right. So what do we need? Well, we need obviously a direction. Okay, we need the A, B, and the C. We need the point x0, y0, and z0. Okay. Now, and in some cases, you'll find that okay. So, well, if you like, C might be 0. Okay, so it might be just parallel to say AI plus BJ. Then, if C is 0, we can put a C0 here. Z is equal to Z0. It just means that obviously the line, okay, Z is always Z0. So this line is on the plane, on the Z plane. Okay, all right. This hopefully will become a bit clearer when we do some examples at the end, okay, where we get the A, B, and the C from. Now let's go into the planes. Okay, so we're now going to look at the equation of a plane. Now, you can see here, this is the equation of the plane down here. Now, how do we get the equation of the plane? Now, this is the plane here. Okay, basically it's ax plus by plus cz is equal to d, some number. Okay, you can make the d, put the d on this side, make it equal to 0 if you want to. But how do we actually generate this equation, okay, of a plane? Okay, so what do we do? Well, okay, so we need a point on the plane, x0, y0, z0, and we just say, okay, let's assume that x, y, and z is another point on the plane, and we generate this vector here. Okay, this is just a free vector from x0, y0, z0 to a general point on the plane. Okay, oops, can't see that actually. It's gone off the screen there. Okay, but this is the, let's try and move it across the middle maybe. Okay, oops, what happened there? Try again. Here we go. Now, wonder if this works again. Okay, so basically, this one here is, let's see if this works. Okay, yeah. Ooh, okay, that's a bit better. Okay, so it's basically the free vector on the plane, okay, from x0, y0, z0 to a general point x, y, z on the plane, I, j, and k being, okay, x unit vectors I, j, and k in the x, y, and z directions. Okay, all right. Now, we need a normal vector to the plane, okay. This is, sometimes we can use this, the cross product to get normal vectors, okay, and we're actually going to use a property, I guess, of the dot product, and if the perpendicular vectors are, remember the dot product has a cos theta, and if they're perpendicular, cos 90 is 0. Okay, well the normal, this is the normal here. Okay, we're going to need a normal, okay, because we need the a, b, and the c from the normal to get, you can see here, the equation of the plane. Okay, so we need the normal, and we're going to use the fact that the normal, okay, as I was saying before, the dot product with the normal, okay, and this vector here, which we've actually generated actually from the point x0, y0, z0 to another arbitrary point x, y, z on the plane. Okay, so we're going to use the dot product of these two, this one and this one. Okay, using the dot product will give us this thing here. Okay, this is the, remember, the dot product is just the multiplication of the components. So a times x minus x0, okay, and b times y minus y0, and c times z minus z0 equals 0. Okay, so this then can be rearranged, okay, into, wait, the constant on the other side, d. Okay, so this can be our general plane. So the plane, the equation of the plane is reasonably sensible. Ax plus by plus cz equals d. Okay. Okay. All right. So we can see here that the normal is going to be very important in constructing the equation of the plane. Well, let's actually now go through some examples. Okay, the first example is, okay, we want to find the equation of the line through 3 points, A, B, and C. Here you can see I just made up some points. Okay, so what do we need for a plane? Well, we need a normal. Okay, so we're going to have to use a cross product somewhere along the line here, down here, you can see here. Now, the cross product of what? Okay, well, first up, we actually just find, okay, a couple of vectors. Okay, so we just generate a vector like A, B, and say AC. Okay, you can see here form a few vectors, A, B, and AC, and then we just, now if you've forgotten how to do that, basically you just go, let's have a look at AB. You go minus 3 minus 2 gives you minus 5, okay, 3 minus minus 1 gives you 4, and 2 minus 3 gives you minus 1. Okay, down here. Okay, so we just basically form the actual free vectors A, B, and AC, and then we take the cross product. Okay, now the cross product, you have to remember, is the determinant. Okay, so we put the coefficients here, minus 5, 4, minus 1, minus 5, 4, minus 1 down here, minus 7, 3, negative 6. Okay, and then we expand this out, plus, minus, plus, plus, minus, plus, ijk, and we have these little mini determinants, okay, which we know how to expand. Okay, 4 times minus 6 minus 1 times 3. Okay, so it's, let's have a look, 4, 6, minus 24 plus 3, okay, minus 21. Okay, all right, anyway, we go through that. So we now have the normal. So this is actually fantastic. Okay, we have the normal because we're now going to use the dot product of this, okay, this normal, and it's like a general vector on the plane. Now, how do we create a general vector on the plane? Well, we basically just pick A, B, or C, and then go to some arbitrary point X, Y, and Z, and get, okay, you can see here AP. I've just I used the point A to the general point X, Y, and Z on the plane, and then we do the dot product of this, if you like, general free vector with the normal. Okay, so it just becomes, you can see here, minus 21 times x minus 2, minus 23 y times y plus 1, and then 13 times z minus 3. Okay, and we rearrange this to get the equation of the plane over here. So eventually we, okay, so there's a bit of a procedure involved, but basically you will need the cross product to get the normal, and then you'll need the dot product with like a general free vector, which you'll have to create from one of the points A, B, or C, okay, to get the equation of the plane. All right, let's go on to the next example. Okay, before we go on to example 2, I thought I'd just show you this in Geogebra in 3 dimensions. You can see here I've plotted the points A, B, and C. Okay, we're now going to create the vector u, which is going from A to B, and then the other vector from A to C. Okay, then we're going to generate the normal. Okay, the normal is actually going to be normal to these two vectors. Let's pop it in here. You actually can't see it. I have to. It's a fairly long vector here. This is the normal. Okay, And the equation of the plane, I'll just put the plane in now too. Okay, so here's the plane. It's a bit hard to see, but in 3 dimensions. But you can see here the normal vector is quite long. It's about 33 units in magnitude actually. But if we actually have a quick look at this, rotate it. I think we can rotate it. And just to give you a look at what's happening, you can see here that basically A, B, and C are on the plane. We basically we create the vectors, get the normal vector, then use the dot product to get the plane. Okay, so this is see here, it's a fairly standard procedure, but you just have to remember. Okay, just get the normal first, basically. Okay, let's go on to example 2 now. Well, okay, example 2 is one about lines, and we're going to, first up, we're going to find the parametric and symmetric equations of the lines through a couple of points A and B, you can see here. And then we are also going to find out where the line intersects or pierces the 3 coordinate planes. Okay, that's the X, Y, X, Z, and Y, Z planes. Okay. Okay, so we're going to try and find out where this particular line pierces those coordinate planes. Now, the first thing is, you can see here, we basically get a vector going from A to B, and we know that the line must be parallel to that vector. Okay, so basically generate this vector AB going from A to B. You can see here, it's just this one here. Okay, okay, that's just a very simple little one, 2i minus 3j plus 2k. Okay, so we've now got the vector AB. Okay, we are also going to need the general free vector, okay, from say either A or B. You'll see here, basically to some general point on the line X, Y, and Z. Okay, and so you can see here I've generated the free vector here. Now, obviously, as you know, if these 2 vectors, okay, are in fact traveling in the same direction, obviously, okay, one can be one's scalar multiple of the other, and we use the idea, okay, basically one is a scalar multiple of the other, okay, so U is equal to basically T times AB, if you like, and so you can see here, like, basically X minus 1 is going to equal 2T. Okay, X minus 1 is equal to 2T. Okay, therefore X minus 1 is equal to 2T. Put the 1 on the other side. Then basically you can see here X is equal to 1 plus 2T. Then Y minus 2 is equal to minus 3T. Okay, so it's basically, well, you can see here Y equals 2 minus 3T and Z equals 2 plus 2T. Okay, basically, now if you use the other point, okay, basically we can just see, okay, then we have our X minus 3 is going to equal 2T. Okay, so I haven't actually written the free vector. This is the free vector from A to the general point X, Y, and Z. I haven't actually put the general vector from point B, but basically the same idea here to get the, if you like, the parametric equation. So you can see here we've got 2 sets of parametric equations for the same line. You might think that's a bit strange, and I'll show you in Geogebra that, okay, they are both the same. But basically, parametric equations of a line are not unique, okay, basically because the parameter can change to different sorts of values. Okay, now what about the symmetric equations of the lines through A and B? Well, okay, you can just see here, this is not too bad. If you like, the corresponding coefficients are in fact proportional, or if you like, X minus 1 on 2 must equal Y minus 2 on minus 3 and equals Z minus 2 on 2. Okay, all right, you can see here coordinates basically are going to be proportional or in ratio, if you like, okay, and the same for B. So these are basically the 2 equations, okay, for the same line. Okay, interestingly enough. Okay, so you'll see here when I show you in Geogebra, okay, this is the case. Okay, so the line actually has 2 equations depending on what point you're using, A or B. Okay, all right, so let's actually go into continue on and try and work out where the lines pierce, okay, the coordinate planes. Well, basically all you do for that is You can see here, if we set z is equal to 0, oops, hold on, I'll just take that out. Okay, for the xy plane, and y is equal to 0 for the xz plane, and finally x is equal to 0 for the yz plane. So you're going to have to basically, first of all, let z equal 0. So if z is equal to 0, basically I think you can do this with either form, okay? So it doesn't matter which one of these you use, you'll get the same piercing points, if you like, okay? But I think I used A, okay, here. So if you let so z is equal to 0, you get what? Minus 2 on 2, which is negative 1, okay? And this is where the negative 1 comes from over here. So then you basically solve each of these parts for the y value and the x value, and you get a point here, minus 1, 5, 0. That's where the line pierces, okay, the xy plane. Okay, and if you let y is equal to 0, okay, the same sort of thing, you get 2/3 in the middle, and you just solve these equations individually for x and then the other way for z, and obviously y is 0, so it's just 7 on 3, 0, 10 on 3. That's where the point where it cuts the xz plane, and similarly for the yz plane, make x is equal to 0 and then solve these for y and z. Okay, as I said, I left it here as a bit of an example. You can actually check this by using the other symmetric equation of the line from B. Okay. All right, now let's finally just have a quick look at this in GeoGebra. Well, okay, finally here we have GeoGebra. We've got the points A and B. You can see here, and we've got the x, y, and z-axis. Z is obviously the blue one, the y is the green, and the x is the red one here. Okay, all right. Now I'm going to put the equation through A first, just to show you. Now, okay, all right. This is the first equation of the line. Okay, and I'll put also the second. Now, if I take this one out and I'll put the second one in, you can see it goes through the same points here as well. So if I put them both on top of each other, it's a bit hard to see, but they both are the same line. Okay, those two symmetric equations are actually going through A and B, and they basically, oops. Okay, just to finish up, I'll change the color of the lines just so you can see. I'll put the one through, okay, this is the first line, okay, the symmetric equation of the line through A and B, okay, using A. Okay, let's take that out. Okay, put the other one in now. And this is the other symmetric equation of the line through using B, okay. And you can see here they're both the same straight line, it's just a different way of writing the same line. Okay, now thank you for watching, and bye for now.